for beta, this beta 1, and again we use our standard formula x transposed x inverted x transposed y1. Yeah? So what we get is the corresponding point estimator b1 hat, and b1 hat is a 2×1 vector containing of these two parameters that we estimated. So in the same manner we have the data vector for y2, yeah, which is defined in the same way like our first data vector. So we have the observations from y2, 1, the second observation until yt for the second asset. Yeah? And again we have the same regressor matrix. What we get is we run simple OLS for the second equation as well. What we get is let's call it b hat 2, which is captures the parameter vector for the second equation estimated via OLS. What we get is then the alpha 2 and the beta 2, yeah, for the second equation here. So, and this is then estimated by OLS, x transposed x inverted times x transposed y2. Yeah? Again, so we have obviously same regressor matrix in both equations, just the y vector changes. So in the first OLS estimation, we use the excess return vector of the first asset, and here in the second case we use the excess return vectors of the second asset here as regressant. Yeah? So we get the parameter vectors for both equations. So then we know already how to get our residual vectors that are associated here with both equations. Very simple. So what we get is, for the first equation, our epsilon hat 1 vector is then defined as, take the vector of excess returns from for the first asset minus x, our regressor matrix, times beta hat 1, which is this guy here. In the same way, we get our estimates, our residual vectors for the second equation here. Very simple. Our epsilon hat for the second asset is then given simply by y2 minus x, our regressor matrix, times b hat 2, this guy. Very simple. So obviously epsilon hat 1 is a t×1 vector, epsilon hat 2 is also a t×1 vector. So we have now to take this away. So hopefully you have made your notes. We need now to take away these guys. So having defined having calculated our vectors, our estimated epsilon 1 and epsilon 2, we can now define our sigma, this guy here, but not inverted, but the uninverted sigma hat is defined as this matrix here. So we take the estimated residuals from the first equation, epsilon hat 1, that we just previously calculated, transposed times itself, divided by capital T, which is the number of observations. Here we have the second element is obviously epsilon hat 2 transposed times epsilon hat 1 divided by t. Here the element, the second element in the first row, is then epsilon 1 transposed times epsilon 2 divided by t. And the last element here, or the second element on the main diagonal, which is the second element in the second row, is then simply, how can it be else, epsilon hat 2 transposed times epsilon hat 2 divided by t. Yeah? So all these are numbers, obviously. Yeah? If you transpose this vector, it's 1 by t times t by 1 is 1 by 1 divided by t. So this is a number. That's a number. That's the, and basically what we have on the diagonal, our diagonal elements, this guy here, that's the variance of the residuals from the first equation. This is this guy here. On the second element on the main diagonal, this guy here, this is the residual variance of the second equation, this guy here. And what is above and below the main diagonal of that matrix is the covariance. It's the covariance between these guys here. So we can write this matrix as sigma square 1, sigma square 2, this guy, and sigma 1, 2, which is the covariance between these two residual terms, and here sigma 2, 1. So that's a 2 by 2 matrix. And of course, the covariance between the first and the second residual is the same like the covariance between the second and the first. So above and the main diagonal are the same elements, so it's a symmetric matrix. And symmetric matrix means sigma transposed is equal with sigma. Okay, just a small comment here. So if we have capital N as n is 30, then obviously this guy here would be a 30 by 30 matrix. So it depends, of course, on the dimension, on how many assets or how many variables you use. So now we have defined our capital sigma hat, which is here in the middle of the test statistic. And of course, to invert this, we just use a MATLAB command later on. So we don't have to do it by hand. I mean, we could do it by hands, but this is what the program will do for us. So we just have to basically to compound these things. We define the matrix, and we then let MATLAB calculate the inverse of that symmetric matrix. So next, let's take this away. So the next step is, or the next question is beta hat. This guy here that appears here and here in the equation. So that's actually pretty simple, because we have already estimated for each equation by equation via OLS our point estimator. So what we do is simply we stack for each equation the corresponding OLS estimator below each other, and this is then our beta hat vector. So our beta hat vector is, in our case, b hat 1 and b hat 2 as defined earlier. And this is a 2 times 2 by 1 vector. Yeah. Well, this is n. So if we have more equations, if our n is 30 and we have 2 parameters here to estimate, then we have obviously 30 times 2. So this becomes a 60 by 1 vector. And this 2 here denotes k, which are our parameters. So if we have the Farman branch 5 factor model, obviously then we have 6 parameters in each equation to estimate, so then our k would be 6. And if we would have 30 equations, 30 times 6 is 180, so this guy would be 180 by 1 vector. Okay? So again, so make it very precise. So here we have the alpha 1, the beta 1 from this equation, then we have the alpha 2 and the beta 2 from this equation. So that's a 4 by 1 vector. Yeah? Pretty simple. So now we have defined our, what is this guy here, this capital sigma. We have defined our what is our beta hat here in this equation. So what remains? Next we have to talk about the r, which we have here. So let's take this away. So what is r? Question mark. So r picks the parameter in the vector beta hat that is tested. So it picks the parameters in beta hat, this large vector here, that is tested. And we know we want to test the alpha 1 and the alpha 2, right? So our beta hat, again, it's defined, it has the alpha 1 as first element, this guy here, this beta hat, as second element, and then we have the alpha 2 as third element, and the fourth element is this beta 2. Yeah? So then it follows that our r must be like this: 1, 0, 0, 0. Yeah? Because this vector here, if you multiply this 4 by 1 vector with this 1 by 4 row vector, it gives us exactly this element here, because these three here are set to 0. So if you multiply these guys, what remains, it gives us the alpha 1. Yeah? And the second row vector here, how should this look like? Think about it. We want to grab this guy here. So this here should be a 1 and elsewhere zeros, right? So this guy looks like this: 0, 0, 1, 0. If we multiply this vector here with this vector here, it gives us the alpha 2, yeah, that we are interested in. Yeah. So this guy here is related to this guy, and this guy here is related to this guy. Yeah? And if we consider now, let us define, so this is our capital R. Yeah. So obviously if we multiply beta hat, or if we multiply R with beta hat, so what it gives us obviously is our alpha 1 and our alpha 2 in a vector, in a 2 by 1 vector. So what is here is this guy here transposed as a row vector, and it is multiplied here with this guy here as a column vector. Yeah? So we will see later why this is so. And obviously this is here below in the denominator of that equation. So if we consider now, let us consider now for the single equation here, yeah, we have our b hat 1, yeah, or we have defined our b hat 1 earlier as alpha 1 and beta 1, yeah, which gives us the corresponding point estimates. And let us define small r, yeah, small r as opposed to capital R, small r 1 0. So this row vector here would give us would indicate us the parameter to be tested in each single equation, yeah? Because this guy here R10 gives us always the first element, yeah? And if we have this vector, but also if we would have the second vector beta hat 2, when this guy here would be 2, if we multiply this guy here